All right, I'll do it like this. Can you hear me like this? Can you hear me? Oh, okay, but before you didn't, I assume. Sorry, a bit of growing pains here. Let me one more time do this.
Hey, Yoni, just a quick question is, oh, sorry, you don't have your headsets in, do you?
Yes, I'm with you.
Oh, okay, sorry. The lecture from Tuesday, is that going to be put online?
Yeah, I tried and I had trouble yesterday, so I'll put them both together today. Okay. Yes.
Okay, thank you.
Yeah, I have the recording, but YouTube died as I finished uploading it. Okay, so you're now hearing me from the laptop, but you're seeing hopefully the iPad. Is that the case? Meaning you're seeing the scribbles from last week, from Tuesday on chapter 2? Yep, good. All right, everybody happy? Ready to start going? Everybody recovered from their project? Yep. I assume the yes is for the happy, not for hearing me. Maybe for both. Good.
There was actually a write-up in the Sydney Morning Herald today about how the government thought they were successful in quarantining people in hotels. So I found that interesting after the project.
Yeah, good. My partner pointed that out to me as well. So I mean, of course, there's distance between the project and real life, but good. I'm glad that you made that connection. All right, let's get to business. Project number 2. Okay. Oh, and you know what? Give me a bit of feedback on the chat quickly. How hard was the project on in terms of time? On 10 being unreasonable and 1 being a walk in the park. You should have given us 3 times more problems. Just how hard was the project? 10 is like unreasonable work, too much time for 15%.
It was probably a bit too much time for 15%, but it was interesting all the same, and I think we needed it to learn the underlying concepts as best we can at this stage.
Thanks, TJ. Good to hear. Okay, 7, 8, 6, and what you said, TJ, 5. All right. Okay, so we'll make the next one that's going to be out this weekend is going to be of a similar size, but you get 10 more points. Okay, but you get 10 more points because you're now better at projects. You've gone through a few growing pains. Okay, let's get to business. Poisson processes, and we'll push on even to continuous time Markov chains today, I believe. So this is what we spoke about Tuesday, and that will be online. So we started with the exponential distribution. I won't review anything dealing with the exponential distribution, but I'll quickly review the Poisson process. The Poisson process is not the Poisson distribution. It is a stochastic process related to the Poisson distribution. Okay, so we spoke first just a bit about the Poisson distribution, and here was the first definition we saw for the Poisson process. Here it is, right here, and it is a stochastic process, n of t. We sometimes call it the counting process because it counts the number of events during the time interval 0t. That's what n of t means. And the statistical assumptions or the stochastic assumption of the Poisson process is where you start at 0, and this is kind of the key thing, that the increment is Poisson distributed, and that is an increment on a time duration of t. Okay, Katie says, can we please have the mark breakdown for next assignment? It makes it easier to understand what you're after. Fair enough. Yes, we'll do. As it comes out. I mean, my goal in life is never to put out an update for the assignment. I failed with assignment 1 and with project 1. I put an update with the marks, but yes. Okay, and 3, n of t has independent increments. So if you take any time breakpoints, then these increment, this first increment and the second one, which you don't see here written, and the third one, etc., up to the nth one, they're all independent. Okay, so you know, a bird flying to my right-hand side now is independent of a bird that flew before. That might be not true because, you know, they might all be chased by a hawk or something. Okay, that's kind of related to the binomial distribution. We saw that. And then we got here to section 221, where we spoke about a renewal process construction of the Poisson process. And the key point is that if you take here the timeline, I'll mark the points in red. This is a point, 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 and I'll mark here in orange the times between point. That's tau 1, the time between point, time between point, time between point, time between point. Those times are IID exponential, okay? And that immediately implies a lot of things. So when you, well, okay, if you construct a renewal process of this type, and you say n of s is going to be the number of points up to time s, then you see that n of s has a Poisson distribution with mean lambda s. Okay, so this is probably something that you haven't seen before in probability, that the exponential distribution is related to the Poisson distribution in this way. Okay, and we also already saw above that the time of the nth point is Erlang distributed. That's gamma with n comma lambda. Okay, that's what we call Erlang. Okay, and later on we have that the increment nt minus ns, and sorry, nt plus s minus ns is itself a Poisson that's a mistake. Is oh, okay, no. So this increment for all t is itself a rate lambda Poisson process, and that shows independent increments. So NNT has independent increments, and hence this renewal construction here is also a Poisson process. Okay, so you could view a Poisson process in this way, in the way that we had above, where you actually require a Poisson distribution, but that seems a bit unnatural. I mean, Poisson just seems like something we pulled out of the hat. Whereas with this construction, you actually start with the exponential distribution and you get the Poisson distribution and the Poisson process. Okay. Stop me at any time for questions. Now, this section 222, more realistic models, well, that will speak about situations where you have dependence or time varying things, etc. And I will just skip that. And I want to move to the next section, the compound Poisson process. So compound Poisson process is a generalization of a Poisson process. Okay. It is no longer, and this is also something we're just skimming through. Okay. So I'm just kind of describing this briefly so you see it. Anybody here aspiring to be an actuary? Good. Okay, you're all good people. None of you aspire to be an actuary? Some of you? Nobody? Okay. I mean, it's fine. Even if you're aspiring to be an actuary, that's fine. They're not bad people. Anybody not know what an actuary is? Actuary, I'll put in the chat. Actuary. I think you're right. Probably misspelled. Actuary. So insurance stuff, right, Oscar? Insurance stuff. So there are only 3 unis where you can study that stuff. In Australia, I agree, and that, in my view, is Macquarie, University of Melbourne, and is the 3rd one Bond? Probably. I'm not sure. Yeah. Okay, got them right. Yeah, I started studying this a while back, but then I went on to do a PhD and I didn't find it exciting enough, but it's an interesting job. So what these people do is they do a lot of applied probability and statistics in insurance. And when you look at, and there's kind of generally 2 types of actuaries. There's kind of people that work with life insurance and pensions, and they look at death rates and things like that. And there are actuaries that work with general insurance, meaning travel insurance and car insurance and home insurance and all those types of things. Something happened to the recording, so I'll go back. All right, so for the general insurance actuary, okay, the compound Poisson process is often the key first model they look at. And instead of reading the story that's told there, let's just look at the equation. This is the equation, okay? So, and let me just write it like this. All right, that's the sum of I1 to N of T of yi. Okay. So what this is, you've seen this type of object before, probably in a STAT3004 example or something like this, when this was just n, when you didn't have this t component. Okay, and this is what you'd call a sum of random variables, but the number of summons is random in its own right, so that's what you'd call maybe a random sum. Okay, and you know you did such things such as a computation of E of S is E of n times E of y in cases where these yi's are IID, for example. Now, the compound Poisson process simply says, well, we're not just going to have an S, we're going to have an S of t. I'm going to have an S of t, it's a function of time. You see, it's a function of time, t. And as time goes by, the number of summons that we add is a function of t. Okay, it's n of t. So you have more and more summons. Okay. Now this suits the typical situation of, say, home insurance, because what you'd say is that each claim of a home insurance, so if, knock wood, if somebody's home burns down or something like this, they make a claim of size yi. So you'd have your yi's or IID distributed, which are the claim size. And you also have a Poisson process of claims, and that Poisson process is n of t. Okay, so claims come. So in total, what you have is S of t. Okay, so the total claim size that an insurance company sees can be, at least initially, modeled as this thing called the compound Poisson process. Okay, so the way you'd draw it maybe is something like this, where you'd say, okay, this is time. This was your first event. So up to the first event, you didn't have any claims. Now you had your first claim jump, and that's at size y1. And this is this point, and this is here y of t. Sorry, S of t. Okay, and here you had your second claim, and you had another jump of size y2, etc. Okay, so at any point, what you see is S of t. All right, that's a compound Poisson process. Is it a counting process? No longer. Of course, it's a generalization of a Poisson process, because if we make our random variable yi equal 1 with probability 1, all we have is just a Poisson process. Okay, so that's what we call compound Poisson process. We probably won't deal with that too much, but good that you knew about it. Questions? All right, now let's speak about transformations of a Poisson process. So there are two things that we can kind of do with Poisson processes. There's two standard transformations. One is to thin a Poisson process. And by thinning, what we mean is every time we see an event, we're going to flip a coin independently of everything else and say that event is of type 1 or of type 2. Or maybe we'll flip a multi-valued coin and say it's of type 1, 2, 3, 4, 5, 6, 7. Okay, it's as though I'd be looking here to my right. I'm looking at a bird. Okay, it's a, geez, I don't know the names of any birds. So I'll look here to the right, and I'll look at a marsupial, and I'll say, oh, it's a wallaby. No, it's a koala. No, it's a kangaroo, etc. So I'm thinning according to that. So I'm getting the sub-process of koalas. Oh, geez, these are bad examples. Okay, so the way you could view it is you take your thing, you flip a coin, you take your process n of t, and you've got n1 of t here and n2 of t here. So every time you had a point in time, it was either of type 1, say, or of type 2. Okay? So the result that you get from this is if you do these splits in an IID manner, meaning that every time I get a point, so on the timeline, if you'd like, these are points on the timeline, okay, with exponential times between them, etc. But say that these ones that I circled happen to be of type orange, and these ones here, let's put another one here, happen to be of type purple. Okay, so purple, say, and orange. Okay, I think you get the idea of thinning. Simple. Okay, and of course important, right? So you have customers presenting according to Poisson process. Maybe they are female, maybe they are male, maybe they're of a different gender. Okay, so that's one thing you can have, right? Or this thinning is kind of very natural. And if you believe that, you know, every time you could model things as just flipping a coin and you have one type or another, then, you know, the question is, what are now these processes? What type of process? What's this thin stochastic process? Okay. So the result is that these two processes, or these J processes, NJT, are, first of all, independent, okay? So this one is independent of this one, which sounds a bit surprising. I mean, they both came from N of T, right? But they're independent. And they are each Poisson processes only with a lower rate, with a thin rate. Okay, this is a rate, okay? So you took the original rate, lambda, and you multiplied it by the thinning probability, the probability of that yi equals being of type J. Okay, if you just have two, then you'd sometimes just write here, you've got lambda p and lambda 1 minus p, for example, right? If p is the probability of yi being of type 1, and 1 minus p is the probability of yi being of type 2, for example. Okay, so that's called thinning a Poisson process. So it gives us a way to kind of do a bit of a modeling with Poisson processes where we take a stream of events and we split them up into different events. And of course, you can continue to do this further on if you see fit. Why is this remarkable? Well, I don't know. I mean, I've been in applied probability too long to think it's remarkable. It just seems like an obvious thing. Okay, but here you should read the surprises here. I mean, the surprises here are that both of these came from that. Let me actually say why it's expected, why it's not remarkable. So if you look at this timeline here, okay, so look at this timeline here with T. Remember when we had the binomial view of what's happening in a Poisson process, then we kind of split up the time into these micro little segments that I'm kind of putting on the timeline. And in each one, we have a little coin flip, a little experiment, okay? And with a very high probability, nothing happens, okay? So in each time interval of size delta t, with probability roughly 1 minus lambda times delta t, which is, all right, almost 1, nothing happens. Okay, so in each little experiment here, little coin flip, nothing happens. I'm looking to the right, no kangaroo, not a surprise actually. All right, but with the probability lambda times delta t, which is a complement, you know, we have a event. Okay, I'm looking to the right, and maybe it just, and look, the event happened here on this specific interval here. We were lucky there, right, on that specific interval where I'm zooming into. Okay, so that's kind of what happens in a Poisson process. And the thing is that all these little micro events are completely independent of each other. Now, when you're doing thinning, what you're doing is when you get such an event, you further say, well, I'm now going to say with probability P, I will have a type 1, for example. And with probability 1 minus P, I'll have a type 2. So you can split this up and just say lambda times P times delta T, you have type 1. And lambda times 1 minus P times delta T, you have a type 2. Or if you have many types, then instead of P and 1 minus P, you just get this probability here, which let me see the screen refreshed up there. Yeah, okay, so that's kind of what's happening with the thinning. Still, we can prove it, but I won't do it now. I'd ask you to read this proof. Okay, so it simply uses the basic principles of the computation, and this proof actually shows that each of the sub-processes is a Poisson process. Okay, so this is certainly read this. You'll need that. I mean, the math is simple. Okay, and important. Questions? Okay. Now here, there's a statement that says, the thinning result generalizes easily to the non-homogeneous case. Well, I actually skipped the non-homogeneous case, but it's important you actually know about the non-homogeneous case. So the non-homogeneous case was in the section above, which is more realistic models, above compound Poisson process, okay, more realistic models. And without going much into details, the more realistic, and don't get me wrong, Poisson process is extremely realistic for the right time frame. But if you are looking at, say, events during a day, a full 24-hour day, and you're looking at people arriving to a hospital, then, you know, people don't arrive at 3 a.m. at the same rate in which they arrive in 9 in the morning or midday, okay? So what you would do is you would model the events using a non-homogeneous Poisson process. Non-homogeneous meaning it's not constant of time. The rate depends on time, lambda r, okay? So maybe you'll take like a periodic lambda r, which is for every 24 hours, depending on each case, okay? So this is a generalization of a Poisson process, which is useful. It retains some of the properties, but not all properties. We won't spend time on it just now, okay? That's kind of this more realistic one, okay? So lambda r in this case is a deterministic function, which is the instantaneous rate of arrivals at time r, okay? And what it means is, yeah, that's what it is, okay. All right, so when you do the thinning, what they're telling us here is that thinning, and I'll leave this to you to read, is also relevant for a non-homogeneous process. And this MG infinity Q, we'll speak about queuing, queuing theory. Queuing is in the theory of standing of queues next week, or probably next week. Okay, so this is all an example of MG infinity Q, so this is kind of just a skim through. Okay. All right, so we've seen how to split a Poisson process into two, okay, or into many. The other things we can do is then add Poisson process, so superposition, okay? To superimpose things means to put them on top of each other and add them, right? Superposition of functions, you know what that is, okay? Superposition. So here's the main result. So suppose you have k independent Poisson processes, each with their own respective rates, okay? Then the sum of these processes is itself a Poisson process with the sum of the rates, okay? And it's expected that would be the case. Let's see it. Let's just again draw something, a simple something. So we'll go on the timeline here, and we'll say I'm putting here the Poisson process of koalas that I'm seeing on my right. By the way, a very long time between seeing koalas, rare, but never mind. And now I'm putting here the Poisson process of seeing kangaroos, the blues, okay, so koalas are black, kangaroos are blue. The combination is a Poisson process where if the koalas had the rate, since I'm in blue, the kangaroos have a rate lambda 2, and the koalas have a rate lambda 1. So what I'm seeing is still a Poisson process, okay? So just to get your mind clear, so that for the first Poisson process, the time between events, the mean time between events, was 1 on lambda 1, because that's the mean of an exponential distribution, right? So when the rate is big, the time between events, so when the rate is big, the time between events becomes short, or vice versa. For the second process, the time between events is 1 on lambda 2. Now we have a Poisson process, which is like everything. So I'm just draw everything in red, okay? So I'll call that n of t was n1 of t plus n2 of t. And the mean time between events is 1 on lambda 1 plus lambda 2. So we sum up the rates. Okay. So that's superposition. All right. Yeah. It's a superposition of Poisson processes. And this concept is actually going to be important when we get up to continuous time Markov chains. So I hinted about continuous time Markov chains on Tuesday, and we'll get to it still even today, I believe. Yes. So you guys live Markov chains at the moment. So think about this situation. You are in state 1 in a Markov chain, and you can go into state 2 into state 3. Okay. No longer discrete time. You can go at any time instance. Okay. So you can either go here or go there. Right. Remember, I spoke about continuous time Markov chains when we spoke about the exponential distribution. I called this random variable S and this random variable T. And these were random variables where we had like a race between the time until going to 2 potentially, or the time until going to 3. And the state we're actually going to go to is the one that's minimum between S and T. So we're going to stay in time 1 for a duration that's min in state 1. We're going to stay for a duration min S of T, at which point, depending on who won the minimum, is the minimum attained by S or attained by T, we will go to 2 or 3 respectively. Okay. A different construction. So I'm kind of going to the future here, continuous time Markov chains. Okay. But that's what we're doing. Just discussing it at this point. So you kind of get your understanding. A different construction would be that you're now in state 1. And you all the time have this little Poisson process that's pulling you to state 2. But still nothing's happened. So sometimes people call that a Poisson clock. You're like in state 1 and I want to go to 2, but you're still not going. You're not going because you still haven't had an event on this Poisson process that goes to 2. And in parallel, you have another Poisson process that pulls you all the time to state 3. Okay. So anytime you can either go here or go there, but you still have it. I mean, you're still here, because if I'm drawing now, I'm now drawing a timeline. Just say you're in time 0 at state 1. Okay, nothing has happened on the Poisson process that pulls you to 2 or pulls you to 3. So now I'm going to put the 2 events. Let's say this is an event that went to 2. Let me color code this a bit. I'll do this 2 like this, and I'll do the 3 like this. So you got the 2 random variables. Okay, so you got your T, you got your S. Okay, that's the 2 exponential random variables. So, and you've got a Poisson process, and let's call it N2, and you've got a Poisson process N3. Okay, and battery is very low, very bad. Let me plug in 1 second. I tried to charge this all morning. Nothing works these days. All right, and this is N2. Okay, and you've got here, let's say this was the first event of N3, okay, and here was the first event of N2. I mean, there'll be further events on this timeline, on this joint timeline, but they actually won't matter because we've already we'll be leaving state 1 by this time. So we're all the time in state 1, and we're subjected to these 2 Poisson processes where the first one in which there's an event, we're going to move to that state. So we'll move then to state 2, or we'll move to state 3, either to 2 or to 3, either to 2 or to 3. In this realization, where are we moving, to state 2 or to state 3? To state 2, Ned says. Thanks, Ned. Okay. Moving to state 2 because S happens to be smaller than T. Okay, so we're moving to state 2. This is the time until state 3. Okay. Now, you can say that the time that you're in state 1 would be the time until the first event in the superposition of these two processes. And we just said the superposition of these two processes is going to be a Poisson process with the sum of the rates. Okay, so now you kind of treat this whole timeline you see here as one Poisson process, which is the Poisson process until you've left state 1. That's it. Okay. That's kind of tying this to continuous time Markov chains, which we'll see more formally soon. Continuous time Markov chains. Questions about this? All right. More nice properties of Poisson processes. And this one's nice. This one, like, it's like, I remember the year was 1999, I saw Poisson processes for the first time. And then I was like, oh, wow, they involve the exponential distribution and the binomial distribution, as you saw, and the Poisson distribution, obviously, but also they involve the uniform distribution. They also involve the binomial in a different way. So let's look at this theorem. And this is really the theorem that kind of makes you feel that a Poisson process is really the most random way in which you can think about putting events on the timeline. So let's read it carefully. So if we condition on nt equaling n, okay? What does it mean to condition on nt equaling n? To condition on nt equals n means that I know that by time t, there have been n events, okay? So we've been now sitting together for 33 minutes. You've been watching me. And let's just say that, you know, Matt Richards sitting there is counting my eye blinks. You know, I'm sure he's not doing that, but, you know, he's kind of putting events on the timeline. And now we're at time 33, so t is 33, and n I've had 517 eye blinks. So, you know, so Matt has seen that by time 33, okay, I'll make this continuous, 33.5, you know, in 33 minutes and 30 seconds, 33.5, he has seen that I have had 517 eye blinks, okay? Eye blinks are sort of like a Poisson process. I mean, there's a bit of kind of relationship, but it's a Poisson process at first good approximation. So 33 minutes, 0.5 have passed, 517 eye blinks. Now let's look at the vector of the times of eye blinks, given that I've reached this number of eye blinks. I mean, obviously we're not guaranteed to have 517 eye blinks. If in a different lecture, a different place, a different realization, but time 33.5 would have a different number of eye blinks, most probably. Okay. So this distribution T1, T2 up to Tn is going to be a uniform distribution. That is what this theorem says. But to do that, it has to speak about order statistics. You know, I'll explain that again. Okay. So let's see. I'll draw a drawing again. A lot in drawings today. So the drawing is, you've got your timeline. This is time 0. This is some given time t. You know, and this I'll draw it like this now. I'll draw n of t. You know that n of t has reached a certain level, n. Okay, that n, you know it. That's your condition. Conditional on the fact that the process is here at level n. Okay, so that means that there are n events someplace here. Okay, n events. So the distribution of these events is now going to be uniform. So there's actually no information. They're not more skewed to the right. They're not more skewed to the left. They're uniform. But we can't say they're exactly uniform because we know that the first event is going to be before the second event, and the second event is before the third, etc. So what they're going to be are going to be like the order statistics of the uniform distribution. Let's see that in a second. But still, I want you to understand it. What we're saying here is, given that you've had n events, then we actually know nothing about where these events are on the timeline more than just that they're uniformly distributed. It's not that more where at the start or more where later. And this really kind of can convince you that a Poisson process is the natural, most random, non-informative process of events over time. I mean, because before speaking about Poisson processes, I would have asked you, hey, can you give me, how would you say the distribution of random events over time? And you'd say, well, I'd want it to be uniform. But then I'd say, hey, come on, buddy, or buddy, yes, uniform is on 0t or bounded, right? You can't do that. But here, if you condition on the fact that 0t you have, then events are going to be. Okay. Is the point clear? Yeah. Okay. So now let's look at a bit more detail. So the times we're speaking about, this is the same notation we had before. These were the arrival times. Okay. And U's are actually going to be uniformly random variables. Okay. Now, when you take n uniform random variables on some time interval, and then you can reorder them. I'm hoping you did this in some stats course or another. What you're doing is the order statistics. Okay, so after you reorder them, so you say V, you're going to reshuffle them. Has anybody not heard the phrase order statistics? So like in statistics, if I take a random sample x1, x2, up to xn, and then I write x, have you seen this notation? Has anybody seen or not seen this notation that I'm doing now? So this is a random sample in stats, and this is the order statistics of the random sample. I've seen before. Matthew's seen before. Thanks, Matthew. Hello. Okay. And Alistair is not. So we've got, and Katie have not, and Peter have not. Okay, so many of you have not seen it because you just haven't, and that's fine. So you've done some stats course and you've seen a random sample, right? That's the observations. I mean, when you get the observations, let's say if you want to compute the minimum or the maximum or the median or Q1 or Q3 or the interquartile range, what you're going to do is you're going to sort them. So STAT3004 mentioned it. Yep, thanks, Isabel. Right, yeah, I think it'd be in a course like STAT3004. Okay, so you're going to order them, okay? So basically, the way you do it is you just need to say that this one is less than or equal than this one, and that's less than or equal than this one, and that's less than or equal to this one. So you know, when I say x17 with like brackets here, what I mean is x17 equals some xj. Okay, there is a j that equals xj, where xj is less than x18 and greater than or equal than x16. Okay, so I mean we sort them all together. So it's called the sorted order statistics. Okay, so or here the author of this book didn't want to draw on your statistical knowledge. He was probably right. Okay, and what he wrote is he said V1 up to Vn. Okay, there's a missing a lot of typos, and there's a missing greater than V1 up to Vn are arranged in increasing order. Okay. So the theorem says that the vector here of T1 up to Tn has the same distribution as the order statistics of the uniform distribution. Okay. Now you can now play around a bit and think a second. What are the order statistics of the uniform distribution? So for this, let's just take n equals 2. All right. Let's take n equals 2, and I'm giving you two uniform random variables, u1, comma u2, which are distributed on uniform IID on the interval 0t. Why? Because I'm assuming, let's just say that by time t, there have only been 2 events. Okay, 2 events. So the joint distribution of u1, u2, I'm now going to draw here. This is 0t, this is 0t, is going to be a density above this plane, right? But if you want to go from that into V1, comma V2, okay, which are the order ones, okay, so I just want to say V1 according to the notation I spoke about above is U, oh, don't start this bad thing, iPad U1, and V2 is U2. So V1 is like the minimum and V2 is the maximum. Okay, so if I'm, no, don't die, I charged you. V1, uh-oh, I'm getting bad vibes here. V1 is going, and this is V2, okay, I should now write less. V2 is going to just have a distribution over this area. I'm now wasting all my pen battery on this, okay? So that's how the joint distribution of V1 and V2 is. All right, think about it, because and it's still going to be uniform over that area. Okay. So the proof of this is also another thing that I'm not going to speak about now. He wrote here, the author wrote it as why it is true. Okay. But it's another one of those proofs that I will add this to the self-study guide that you really must follow yourself. And then I'm happy to answer questions in the visit hour. Okay, is the property clear? So the property shows that effectively what you're saying is the times of events are uniformly distributed. But you can't just say that the time of events, it'll be wrong to say that the time of events T1 up to Tn are just independently uniform distributed, because that's not true. T2 is always going to be greater than T1, and Tn is always going to be greater than Tn minus 1, etc. All right? Okay, so let's move on to the related property, which is also very nice. I mean, this one, also one of my favorites, almost an all-time favorite. It's related. Okay, so all these things should make sense if you kind of feel a Poisson process. So please, now when you kind of live your life now, look for Poisson processes all around, or things that you would explain using Poisson processes. All right, so if S, and now my pen is low. I'm sorry, I spent a whole lot of time charging it. I actually have 2 pens. Next time I'll charge 2 pens. These are Apple pens. I don't know, maybe it's because I have a contact tracing app running in the background and my pen is kind of spending all its Bluetooth energy listening to the bullshit that the app is saying. I'm not sure. All right. Probably not. All right, so if S is less than T, so now take 2 time indices. Now take 2 time indices, S and T. And if one is less than the other, so just, I can't even draw here now, I'm sorry. So you take a time S that's less than T. And you take M that's less than or equal than N. So look at this probability, and I'll just highlight it by zooming, okay? I'm sorry, I cannot draw anymore. Oh, I guess what I can do is annotate on the Mac. That's here. No, I cannot. Okay, enough messing around. All right, so just look at this. What does this say? This says you now know the same thing that we knew before, that by time t, we had n events, right? So after 33.5 minutes, we had 517 events, or whatever we said. Okay, now we're saying, now let's look at a smaller time, s, and say, what's the chance that up to that time s, we had m events? Okay, m must be less than or equal than n. So it's going to naturally be binomially distributed with parameters n and success probability s on t, because you have uniform times happening up to time t, right? So the chance of the m events happening before time s is s on t, okay? Is that clear? So that's, so it follows immediately from this thing that you have now these, from this illustration that you have here, you have uniformly n events, and now you're asking how many of them occurred up to some time s, which I cannot draw you anymore on this, but is up to some time s. Okay. All right. Questions about this? And again, these proofs, they're all good Poisson process practice. I mean, they're not these kind of out of the blue proofs. Okay, and that's it. That chapter summary now summarizes Poisson processes. Right, so with this, we've got, well, officially 4 minutes. And no pen. Let's go to this chapter, SP4. And we'll be spending most of the rest of the semester on continuous time Markov chains. Okay, that's, and we'll actually have time to do a bit of measure theory a bit towards the end, right? And then you'll have your problems, problem session and the 24-hour exam. And then we adjourn. All right. So no questions about Poisson processes? You guys still hear me, right? It's been an extremely, yes, thank you. But who's, okay, thanks. Thanks, Matthew. All right, good. So continuous time Markov chain. You already know what to expect. You don't want to live in this kind of world of discrete time because, come on, time is moving continuously unless it's not, okay? Unless you're going periodically, etc. So first equation in this chapter here, what you see in the top, I'm moving now to the top, is what you'd expect of a Markov chain in discrete time, okay? Look at this one. This is the one at the top. Again, I can't directly point to it. It's this guy at the top. Okay, so if you know the nth event, this was discrete time. So you know the nth state, the state at time n. You know that was I, and you also know a whole bunch of history. You have that in-1 up to I0. You know all kinds of history. That just equals the probability on the right-hand side because history doesn't matter. Okay, only your latest point in history matters. That's the Markov property. In continuous time, you'd now think of a stochastic process X that still takes discrete levels. Okay, so continuous time Markov chains, they still take a discrete state space. Okay, it can be finite or it can be countably infinite. Okay, but it's not a continuum of space. I mean, there's also processes of continuum of space because, say, if you just do a random walk when you add, a continuous random variable, then you could step on every point in the line, and that's a continuous space Markov process. But we're still going to be in discrete states, so there'll be like the number of people that are sick or something like that, or the number of patients in a hospital, or the number of people in a place, or anything like that, or the weather. However, the time index here is T, continuous, okay? And what you see here is, again, the Markov property. So now, if you have XS, at time S, you saw the process was I. That's what you have on the left-hand side. And you also know at different other times, Sn, Sn-1 up to S0, different levels of the process, okay? You knew what it was. Where all these S's are smaller than S. So look now at the top there, scroll up, all those S's are smaller than S, okay? And you're asking, what's the probability that we're in state J at time T plus S? Well, it's just going to be like moving from time 0 to time T, because that's a difference from I to J. And that assumes that we're homogeneous as well. So this is what a continuous time Markov chain is, very loosely, all right? Now, the first thing that this chapter does is treats the Poisson process in its own right as a continuous time Markov chain, okay? The state space of the Poisson process is going to be 0, 1, 2, 3, 4, up to infinity, countably infinite state space, okay? And you move between states, okay? But you only move up in a Poisson process. It's a pure birth process. Poisson processes are also important, just as I alluded to earlier, for describing the dynamics of continuous time Markov chains. The next thing this chapter does, so I'm going to continue on this Tuesday, and you'll get a slightly more revised self-study guide now for the second half of the course, okay? Is speaking about these probabilities that you see at the top, okay? So do you remember with discrete time Markov chains, we had our transition probability matrix, where in one step, how we moved from state I to state J, that was the ijth entry of the matrix. Now you need to speak about time. Okay, so what is the probability of moving in t time units from state I to J? So in a sense, this p subscript t I j, you could say that for every t on the continuum, you have here a matrix. Okay, that's a lot of data to write. But that's not how we're going to specify the process, because it will be kind of a much easier specification. So the parameterization of the process is going to be small. Okay, but these will be the first probabilities of interest. And I'll just go with these equations. So I'll come back to this when we meet Tuesday. The Chapman-Kolmogorov equations, they look just like the discrete time analog that you already saw for the Chapman-Kolmogorov equations, okay? And they actually help define these probabilities, okay? So we're saying on the right-hand side, what is the probability in S plus T units to move from state I to state J? Well, we need to look at all intermediate states K at time S, okay? And we'll do then the law of total probability. That's a Chapman-Kolmogorov equation. All right, so I'll take it from the top of this chapter, armed with a good pen Tuesday. And then Tuesday at 2, there'll also be already the visit hour. With the tutors today, you're going to speak about Poisson processes. Questions?
Thanks, Johnny.
Matthew's asking, will you upload this update schedule really soon? Yes, it will. Manhusa's asking, what's a tutor Zoom link? So that's on Blackboard. Let me actually, my Blackboard's open, so I'll make your life easy. Maybe it's not easy. Maybe somebody can send a Zoom link to Manhusa just to make. Oh, okay. So here, no. Let me share the screen here so you see it. I'll share the screen on my computer. So just so you see the tutor Blackboard. So share my screen now. We can do this. Okay, so these are the Zoom tutorials today. Evan is starting in 6 minutes in these links. You see the numbers, I hope. Okay. Now, I've also asked my friend and colleague, Daryl Daly, to mark one assignment. It will be the assignment which I think is the best assignment. He hasn't responded yet. I mean, he's well and truly in his 80s, but he's a great mathematician. So he wrote the book of epidemiology with Joe Gani. So maybe one of you will have their assignment marked by Daryl Daly. We'll see if it looks very impressive. Assignments look great. All right. If no questions, then bye-bye. And here's
Yoni.
Yes.
Sorry, I think this might be like helpful for everyone, but I'm still sort of just having a bit of a difficulty with understanding the difference between skip, skim, and read. Is there sort of like a good way of describing what you intend by those three terms?
No problem. I mean, read means to, read every character that's there and make sense of it. Still, it doesn't mean that you have to know it by heart if you're woken up in the middle of the night, right? I mean, the exam is a 24-hour exam, etc., right? But you might have to recall on some of these sections in the exam. Okay, but read actually means that you immerse yourself in this material. So some of the proofs in read are a bit complicated, etc., right? So, but it still means to read. Skip means completely skip it. Just don't look at it. Okay, that's skip. I mean, you can look at anything. We're all free people, right? But it's not kind of the best choice for the course. All right. Skim means to look through so you're aware of the concepts, just for kind of your general knowledge. Okay, and maybe there'll be a related question to it or something like that, but that's not the focus of the course. So skim means, you skim through and you tell yourself, oh, what was this about? What is this about? I mean, the more you do math, the more you're able to skim through things and kind of get a general feeling about them. But that's, so for example, I think reversibility was, let's see a second. So, self-study guide. And I'll update the self-study guide now to have more details for the second half of the course. But when we're here, yeah, like detailed balance equation. So it's, you know, say if you end up doing an honors or something else and you find yourself in a seminar and they say, oh, a detailed balance equation, have you ever heard about it? Okay, you've heard about it. Okay, but maybe you haven't done the exact same. That's kind of too skim. Okay, similarly with reversibility. I mean, each of these things is a big topic in their own. Okay.
Hey, Yoni, with the exam, is that going to be like you have just 24 hours to do it, or will it be like you can start it at one point, but once you start it, you have 2 hours to finish it?
No, it'll be 24 hours. So there won't be work that you'll need to battle for 24 hours, but I think it'll be like 60 or 70% should be doable within a 2-hour type thing. And then, you know, another slightly more difficult thing that may take 2 or 3 more hours, but it's just open 24 hours. Spend all 24 hours on it if you'd like.
All right. Cool. Thanks for that.
Exams is now giving me trouble with that, but I'm quite sure we'll be okay with it. All right. Other questions? Okay, so I'll put these recordings up now as well. Have a good one, everybody. Bye-bye.
Thanks, Yoni.
Thanks. Bye.